Hello everybody, this is Mostapha Kalami Heris from Yarpiz, and I'm going to discuss with you the random key encoding. As the name suggests, it's a way of encoding, but what it encodes? It's a way of encoding solutions for optimization problems, solutions of which can be represented as permutations, like Travelling Salesman Problem or TSP, or Quadratic Assignment Problem, or Vehicle Routing Problem. All of these problems actually have solutions in discrete space and they can be represented as permutations. But generally, we have some algorithms which are continuous, which are searching in continuous space, and encoding solutions which are permutation like in continuous space requires a way of encoding, requires a way of representing discrete space with the constraints of permutation using real numbers or continuous numbers. And one of the methods to do this is random key encoding. It's very simple and it's very useful. And if you learn this, you can represent solutions of discrete problems like TSP, QAP, VRP, and dozens of problems which are very useful in real-world applications. You can solve these problems using continuous optimization algorithms. And we're going to discuss this and see how this works. First of all, for example, let's assume that we have a TSP problem, and these are, for example, our cities, our locations, and we need to find a path that goes through all of these cities, all of these locations, and is shortest. A salesman tries to visit every location and once and travels the minimum distance possible. Okay, for example, this is a solution for this. Let's number these 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We have 10 nodes, and for example, we start from 1, then go to 2, then 9, then 4, then 3, then 7, 6, 5, 8, 10, and then go back to 1. So this is our start point, and this solution is not optimum because here and here we see that it cuts itself, and simply if you replace these with other edges, it can be improved. But it's a solution, it's a candidate solution. It doesn't need to be optimum. It's a just candidate solution, and if you want to represent this, we can simply write the numbers in the path, and it is going to be a permutation of numbers from 1 to 10, and that is 1, and then 2, and then 9, 4, 3, 7, 6, 5, and and 8 and 10. So we have all of the numbers from 1 to 10 here, and all of them appear just once. It's a permutation. You can replace these with commas and convert to a sequence of numbers. It's a permutation. And we need to be capable of creating sequences like this, known as permutation. It's a typical solution for our TSP problem, Traveling Salesman Problem. But assume that you have an optimization problem, optimization algorithm like PSO, like differential evolution, like continuous genetic algorithm, CMA-ES, whatever. Then how you can use a continuous domain optimization algorithm to create permutations. How we can do that? The key is random key encoding. We're using this. And it is very simple, but yet very powerful. Assume that you need to create a permutation of numbers between 1 to 5. Then just create 5 numbers in a given range, and usually it is in the range 0 to 1. So we have this range 0 to 1, and just create 5 numbers, random numbers here. We're going to create a random solution, a candidate solution. Let's create some numbers. For example, if you use any programming language, you can create 5 random numbers here, or actually pseudo-random numbers. And assume that the output is 0.5, 0.4, and 0.6, 0.1, 8, and 3. Okay, and we know the numbers, the index for each number. I'm writing them here. Then this is the generation of numbers. Then sort these numbers. It can be ascending, descending, it doesn't matter. Usually ascending is better, so we sort these, but we sort the numbers, the real numbers here, and attach the red numbers, the index numbers, to them as well. Okay, so the smallest number is 0.1, and the index is 3, and the next number is 0.3, and the index is 5, and the next number is 0.4, and the index is 1, and next number is 0.6, and the index is 2, and finally the biggest number in the list is 0.8, and the index number is 4. But now you have a permutation. This is our permutation, and we were searching for a permutation. We were searching for a way to create a permutation, random permutation. And because we used these real numbers as keys, and we're sorting those keys to create our permutation, to reveal the permutation behind this, this method is simply called random key encoding, and it is very useful. So, and usually it is it uses the range 0 to 1. It is a standard range to create numbers, and then it doesn't matter. You can create thousands of numbers and then sort them, and then you can create a permutation of length 1000. But you know, if you're familiar with OR and the way they try to represent their problems mathematically, by using this method, you're avoiding all of that constraints, all of those constraints, and it is indeed very useful. So we have just a single step sort, and then sorting, when we're sorting the keys, the values, the integer values attached to each number is sorted, and then we get a permutation. But how, for example, it can be used to solve QAP problem or VRP problem? All of them are permutation problems actually. For TSP it's obvious, but for QAP, in QAP we're trying to assign some items to some other items, and maybe they, for example, we have, for example, some items, some places here, and we need to assign, we have 5 places here, and we're going to assign 2 objects to 5 places. It's the QAP problem, and we can define some kind of task, some kind of cost for each of them, and we can define the optimization problem and search for optimum solution. It is a simplified view of the QAP problem. And for example, let's assume that A ends up here and B ends up here, and all of these are empty. And if we attach some numbers to these places, to these empty assignable locations, then our solution will be like this. It is just simply assign A to place 1, B to place 5, and all of them are empty. But we have 2 objects, A, B, and we have some null objects, and if we write down the numbers here, the number of locations, A is going to be in location 1 and B in location 5, and it doesn't matter, we can use 2, 3 and 4 or any order. You see, this is a permutation again, and you can always create a permutation and then select for example, if you have 2 assignable objects here, you can select 2 of them and then assign the first object to the first number, first location, the second object to second, third to third, and on and on. And it is a permutation. So it's just kind of selection mechanism. And if your algorithm, if your problem deals with ordering items, okay, it's a permutation. And if your problem is kind of selecting some items, it's again a permutation like problem. And sometimes in, for example, VRP, we can also use the permutation scheme. And in VRP generally we have a depot here, and we have some locations, some customers, and we need to assign them to some vehicles and fulfill their requests. For example, this is our first vehicle, goes to these places and then goes back to depot, and this is the second vehicle, and this is the third one, and this is the fourth one. And if you number all of these, you see we have 4 distinct routes for 4 vehicles, and if we want to represent all of these, we need a way of representing this using a sequence. But here, if I want to represent these, let me reduce the size of this, okay, and here I'm going to write down these. First, the first vehicle, it is first vehicle, it is second vehicle, third vehicle, and fourth vehicle. Let's write down the route for each of them. So 1, 2, 3, and 4. This is the route for the first one, and second one is 12, 14 and 13, and the third one is 11, 10, 9, 8, and 7, and the final one is 5 and 6. And you see here we have all of the numbers from 1 to 14, and if we kind of glue these routes to each other, we can create a permutation. But where is the boundaries? So to create a separable list of routes, we just add some items, and it can be written in this format: 1, 2, 3, 4. This is the first vehicle's route, and then add star here. It is a separator, and then 12, 14, 13, and then again another separator, and then 11, 10, 9, 8, and 7, and then another separator, and then 5 and 6. You see, now we have 3 separators, but we can replace these separators with numbers, with artificial nodes, and it can be 15's node, it's an artificial node, and 16's and 17's. We don't have 15's or 16's or 17's location. They are missing. They are artificial. But we have added those, and whenever we reach an item which doesn't exist in our list of our locations, then we know that it is a separator. But here we have a list of a permutation from 1 to 17, and you see this is the first vehicle, this is the second vehicle, this is the third one, and this is the fourth one. Okay, and the number 17 actually is equal to 14 plus 3, and what's the 3? It is 4 minus 1, and we can replace this. It is the number of locations, the number of customers, the number of vehicles, and this is just a constant. So if you want to represent a solution for VRP problem, this is VRP problem, a simple VRP problem, then you just simply create a permutation of size number of locations plus number of vehicles minus 1, and that's it. And that's a permutation, and we know that how we create permutation using real numbers, and the solution is random key encoding. So TSP, QAP, VRP, scheduling problems, all of them, they rely on creating permutations, and you can use this very simple scheme, the sorting numbers and attaching the indices to those numbers to create permutations. And when it's as simple as TSP problem, it's straightforward. When it's a selection problem like QAP, you just create a permutation and then select whatever needed. And if it is complicated like VRP, you can come up with adding artificial nodes, artificial locations, dummy nodes, stars, whatever else, to create or to encode the solutions of the problem. And that's it. With this simple technique, you can solve problems, permutation-like problems with different kinds, scheduling, routing, crosstalk, VRP, all sort of that, using continuous optimization problems, continuous optimization methods. And previously I've provided sample codes in MATLAB and Python on Yarpiz website, and you can download them, you can search them. I also share the source code on GitHub as well. So I hope this video was helpful, and it can help you to solve your own OR optimization problems. And if you have any comments, questions, suggestions, please let me know in comment section. And thank you for watching. Please subscribe to this channel and like the video if you liked it, and introduce the video to your friends. Thank you very much, and see you later.